y equals secant of x, or f of x equals secant of x. So we know secant of x is the reciprocal of cosine of x. So we want to kind of look at cosine, and maybe that can help us determine what secant is. So at x equals 0 radians, cosine is 1. So if I imagine my unit circle, that's the x coordinate on my unit circle. Secant is going to be the exact same thing, 1, because 1 over 1 is 1. However, when you get to pi over 4, cosine of x is 1 over the square root of 2. Secant is, flip the fraction, rad 2. So I've gone from a small amount to a larger amount. Something really interesting happens at pi over 2. Cosine of x is 0. However, when you flip that reciprocal, you get 0 in the denominator, and secant of x is undefined. 3 pi over 4, we have a negative 1 over rad 2. Flip that fraction, and we have a negative rad 2. So we've got a bigger number there. Continue on, you get to pi, negative 1. Notice that secant is the exact same thing, is just 1. So if I plot some of those points, I can look at x equals 0. I know that's going to be 1, so it's sharing a point with cosine of x. Now this is the interesting part, is what happens as we move back and forth. So this blue is my cosine of x, and these red dots are my secant of x. So here, where my cosine of x goes down, my secant of x goes up to rad 2, or about 1.4. So I can see it rising here. Now, wondering what happens as we get close to this asymptote, this line where it can't be. And I can see over here on the graph, my cosine hits 0 here. So my cosecant is going to be undefined there because 1 over 0 is undefined. And I have that all along here, any pi over 2. So even negative pi over 2. It's undefined because I have a 0 in the denominator there. So I can tell by looking at the graph even where it's undefined. It's where cosine is 0. So 1 over cosine would be undefined. So then I'm going to use this as my model to help graph y equals secant of x. So now what's happening, I wonder, as my cosine gets smaller and smaller and approaches 0. So notice right here, if I take the cosine, it's approaching 0. It's getting closer and closer to this x-axis here, or 0. So if I imagine what happens as cosine gets really, really small, I can figure out what secant's doing when it gets large. So let's say I'm getting so close to 0 right here, I have like a 1 over 100. If I have 1 over 1 over 100, that's going to give me 100. Flip that second fraction and multiply. So I'm going to get really big numbers as I get closer and closer to this line, pi over 2, for my secant. So my cosine is going to give me small numbers. I'm going to get small numbers for my cosine, but I'm going to get really big numbers for my secant, and so it's going to approach this asymptote like this. And approaching it. So as cosine gets closer and closer to 0, and that number becomes really small, so 1 over really small number is going to give me a very large number. The same thing happens here when I'm around pi, except for in the negative direction. So as I'm getting negative right here, my secant is still negative, but I'm going to have 1 over a really, really negative number. So secant becomes very negative, and the same thing happens here. And so I'm going to use my cosine to help me draw my secant graph. Now the blue is not my secant graph, it's just the red. And so I could erase my reference cosine, or even dot it, to just kind of show that it's a reference in order to draw it, just like my asymptotes are. They're references too. I don't need to have them on there, and they're not part of the solution set. So this is secant of x. Now let's take a look at cosecant of x, and you can imagine it's going to be very similar. So cosecant of x is related to sine of x. So that's the same as f of x equals 1 over sine x. So it's going to be related to sine of x. And I looked at some values here. Now when x is equal to 0, sine is 0. 1 over sine is undefined. Pi over 4, I have 1 over rad 2. Flip the fraction for cosecant, and I have rad 2. Pi over 3, so I've got some values in between, so you can see a little bit what's happening in between. Rad 3 over 2, flip the fraction, I have 2 over rad 3. And I have a 1 here at pi over 2. Notice that doesn't change. At pi over 2, my sine of x is 1, and my cosecant of x is 1. So pi over 2 right here, they share a point. They share that point right here at pi over 2, comma 1. And so the same sort of thing is going to happen here. As this approaches 0, so I'm going to have my zeros. My zeros are in a different place, though, because sine is 0 at different places. Sine is 0. Sine of x is 0 at x equals 0, and x equals pi, and x equals 2 pi, and 3 pi. So it's the whole pi numbers that will give us a 0, which means the cosecant will be undefined in those places. So over here, I can see that my cosecant's never actually going to equal 0 because I have a 1 over the sine, so I don't have any zeros here. And I notice it shares some points here. So I'm sharing a point at 3 pi over 2 as well. And it's sharing 1. And so then I'm going to connect these. And again, as I look at what happens as sine approaches 0, I have 1 over a really small number. So if I have 1 over a decimal, you can even try it on your calculator. As it gets really, really small, my 1 over sine of x is going to get really big. So 1 over 1,000 is going to equal 1,000. So as I get closer right here, flipping that fraction is going to make it be a very big number. And the same is going to be true in this negative direction. And here as well. And you could keep going. You notice that this is also a repeating pattern, and it has a period. So I go up, and then I go down, and then I go up, and then I go down. So right here, it's going to start to repeat again and continue along the way. Now cotangent looks a lot like tangent. However, I'm going to have my different values right here. So I know at pi over 4, I'm going to have a value of 1 because the sine and the cosine match each other. And then over here at 3 pi over 4, it's negative 1. So my cotangent is going just the opposite of my tangent, and I have it undefined. Cotangent of theta is x over y, my x coordinate over my y coordinate. So I want to look to see where my y coordinate is 0, and that's going to happen over here at pi. When I'm lying flat on that x-axis, I'm going to have a y coordinate of 0, and 2 pi and 3 pi. So I also have a different asymptote that I'm working with. In tangent, you had the asymptote pi over 2 or negative pi over 2, and different halves, because you were looking at where your x value was 0 instead of y. And now I'm looking at where my y value is 0. And then I can go ahead and plot that, and as I get closer and closer, I'm going to go towards infinity. And you can try that on your calculator. You can try to do, find the tangent of 0.1, and then reverse it, and you will get a very, very large number. So you can see what's happening here. And the same is true here as we approach 3.14. You can take the tangent and then flip it, and you will be able to approach that asymptote.